I will be teaching conformal field theory, and so introduction to conformal field theory, but with 2 lectures. It's more like introduction to conformal field theory. And I suppose some of you have taken some conformal field theory lectures before, not like last year, because every year we have this CFT. Okay, so I apologize. I can't get that far in my lecture, and so maybe, as you know, there are many excellent reviews, old ones, new ones, because there's so in research these days there's a bit of revival of conformal field theory, a particular part of it, which is called conformal bootstrap. And so because of this conformal bootstrap excitement, people are putting many reviews on it. And so maybe it's just the introduction to these introductions, and so you can check these papers. So, intro to first motivation. Yes, what is the motivation? Conformal field theory appeared originally from a critical phenomenon. So what is critical phenomenon? What's the keyword for critical phenomenon? Yes, phase transition. Great. Yes. So it's the, and so conformal field theory appears at the critical points. Of the second order phase transition. Yes. And what is that? So instead of first order, it's a second order. And what is the intuition behind it? Okay, so let me draw this. So when you talk about phase transition, in many cases you have some order parameter. And the phase transition means initially, so this is some bed of some field. And initially the bed is 0. But then as you change some external parameters of the theory, then it can acquire non-vanishing bed spontaneously. That's the second, that's the phase transition. And you can model this by this effective potential. So you can think of some effective potential. And so here I plot here my potential will be T C minus T. So my potential is going to be, if you have some function of x, then T minus Tc x squared plus some x to the fourth. So I consider this a photic potential, right? So when the temperature is large enough, then your potential looks like this. This is T greater than Tc. And then if the temperature, T, goes below the critical temperature, then this looks like this. So this would be T below Tc, right? So then what is happening is the stable point of this potential was initially phi equal to 0. Yes? And then as you lower the temperature, then this lowers down to this one because this is going to be the minimum. So this is the second order phase transition. And what is important is what happens at the critical point. Critical point is when the temperature is critical temperature. And so what is happening? So at this point, what is happening? Okay, you have this potential. So T is Tc. This is vanishing. Yes, so that means in field theory, it would mean that the mass is zero, massless, right? So this would be the massless point. So it's a massless. So you will have some massless particle. So this massless, being massless, is necessary condition for having conformal field theory. So people study the theory at this critical point. That's the conformal field theory. That's one motivation. Okay, I think I'm going to go very slow with some motivation, but okay, let me see. So then, second, RG flows. I think Vishnu talked about it in the last lecture, yes? Okay, so good. And so it has fixed points. So in cartoon, it looks like this. So let's say I have two coupling constants, lambda 1 and lambda 2. And then what will happen is, so Vishnu talked about I think, the flowing with the energy scale, right? So let's say I start from high energy, and then I try to understand the effective theory at the low energies. Then for most of the field theories, this is what happens. So you start from some, this is fixed point. This is UV fixed point, and it's conformal field theory UV. And then you have another fixed point. So it's IR fixed point. And you have conformal field theory IR. So as you analyze the quantum field theory from UV to IR, this is what you will see. And so at these endpoints, you've got conformal field theory. So that's why it's important to study conformal field theory. And so what happens to QCD? Let's take QCD. QCD. So QCD at ultraviolet extreme. What is the theory? QCD has, what is in QCD? Fields, gluons, yes, and quarks, right? Okay, so it has vectors and fermions, right? And there's something very well known about QCD at high energies. So what is it? Asymptotic free. Yes, what does that mean? The theory is free. Yes. So this at UV, so it's a free vector. So free. So I have to start from massless quarks. Well, it even doesn't terribly matter. So, but massless vector plus fermion. So this is a free conformal field theory. So free CFT. Okay. So now I want to. So then, what is non-trivial happens is the infrared theory. Yes. So there are several cases. So first, the QCD, what happens as you go to the infrared? Strong, yes. Coupling becomes very strong. And so as a consequence, what happens? Perturbation doesn't work, speaking because it's strong coupling, but no, confinement happens, right? There is confinement. So the quarks in the ultraviolet, they are free. So they are freely propagating. But in the infrared, it confines. And so the typical energy, so that happens around this pion mass scale. So it's confinement, confined theory. So that's one. But it's like here. So in this diagram, what I said is, so this corresponds to energy scale of the pion mass. So then, as you go even further flow down to infrared, what happens? So at this point, there's a typical mass scale, which is the pion mass, for example, or meson baryon mass. It's one of them. And as you go to the further infrared, then any massive particle becomes irrelevant, because if you are probing the energy scale much lower than the mass scale of mesons and baryons, then you can think of these massive particles as infinitely massive. So they decouple from the dynamics. So as a consequence, so this, you end up with an empty theory. So it's a trivial theory. Technically, we call it trivial. So nothing is left as you go to this area. But I have to mention that there is a possibility of having non-trivial conformal field theory. So this picture depends on the number of colors and flavors. Yeah. And it's so. So what happens is, so when you have too many quarks, this asymptotic freedom does not happen. It's asymptotic non-free. So the flavor has to be sufficiently small. So in the actual QCD, you have 6 different quark species. So flavor 6, and color 3, SU3. So it's in this range. So in this range, up to some range, this asymptotic freedom happens. Sorry, so in this range, sorry, the asymptotic freedom happens. But something, so depending on the number of flavors at this lower limit, it could happen that this infrared fixed point becomes non-trivial. And in a supersymmetric case, we know exactly what number these are. But so depending on the number of flavors, the dynamics changes. Okay, but it was a digression. And anyway, so you can have UV or IR, UV and IR fixed point. And that's where conformal field theory is useful. And another example of conformal field theory, what is it? Very famous thing, maybe you know. Okay, yes, I'll come to that a bit later, but before going there, okay, good. So to go to ADS-CFT, you have to know something. So that's ADS-CFT. Yes, but I guess no, my question was the other side. You mentioned N equals 4. The other side is? Yes, string theory. Yes, actually string theory. This is a conformal field theory. In which dimensions? Yes. So this is two-dimensional conformal field theory. So it comes from the fact that, so let's say you have cross string and it's moving in space-time, and then you parameterize this worldsheet by some coordinate. But how you parameterize this coordinate should not matter in physics, right? So the CFT, the conformal symmetry comes from this fact. So it's the, it comes from reparameterization invariance. Invariance of worldsheet coordinate. And so then ADS-CFT, yes. ADS E+1 and ADS-T. Maybe some of you might be working on it. So it's a duality between gravity and non-gravity. And typically it's gauge theory. So the theory, the quantum theory of gravity is the same as quantum theory of non-gravitational theory. I will not go into this, but you will see a little hint of this duality. And one more thing, AGT relation. This is, does anyone know AGT? So this is more mathematical side of this research. And this is the equivalence between four-dimensional, some supersymmetric, like n equal to SUSY QCD, and some 2D conformal field theory. This is also a kind of duality, but this time both sides are non-gravitational. So on one side it's four-dimensional theory, and it's a supersymmetric version of QCD. And also Seiberg-Witten theory, often called Seiberg-Witten. And some years ago, people found that this is actually equivalent to some two-dimensional conformal field theory. So that's where also the conformal field theory studies helps to understand non-trivial physics of QCD. Okay. So this was the context in which a conformal field theory is studied. So, okay, so now CFT, conformal field theory, it's written there. So it's a QFT, a quantum field theory with conformal symmetry. And that's the definition. Simple enough. Okay, so now this conformal symmetry, I think you know some part of it, right? Conformal symmetry includes, for example, what symmetry?
Scale.
Yes, scale. Yes, scaling. So it's a dilatation. Common name is dilatation. This is a scale invariance. So the theory, this theory does not depend on the scale. So in Vishnu's terminology, beta function is 0. Yeah. And other things. Okay, there are trivial. Also, it has rotation, rotational symmetry, and translations. And then I think whoever working with robot knows this special conformal symmetry. Right. This is the scaling. Yes, I scaled coordinate x by parameter lambda. So this is the scaling transformation. Rotational transformation is given by this. This is the antisymmetric tensor. Yes, antisymmetric. And the translation is the shift of the coordinate. And then this is the special conformal transformation. So I define x mu, and Cx is C mu x mu. So the conformal symmetry is not just a scale invariance, but it includes all these symmetries. So you can think of this as saying that conformal field theory is insensitive to which gauge you use to measure length. So you have some gauge to measure the length, and conformal field theory does not care which gauge you use to measure the length. And in equation, this measure, I'll come back to that. No, let me explain this now. Oh. And so how do you mathematically define the gauge to measure the length? Okay, maybe there are a number of ways. Of course, because I know the answer, so I'm asking. Let's say, okay, so this would be the quantity. It defines the length. Length square. This is length square. This is the line element of the space which is endowed with this metric G mu nu. So by this I mean, so this is the length gauge. So then I said, so conformal field theory is insensitive to which gauge to use. And you want to know what does that mean more precisely, yes? So this is what I mean. So I said insensitive to gauges. What it actually means is so what I'm going to do is first to consider flat space. So this is generic, but I consider flat space. I focus on flat space. And then you do this transformation from x to x prime. And then, so what I mean by insensitive to gauges is, so in this new coordinate, so the gauge in this new coordinate is related to the original one by this factor. So you only have this factor. And so this is like stretching and shrinking. So you have some gauge like this, and then you stretch or you shrink, and even if you do that, this theory does not care. So this is what I mean by conformal symmetry. So this is the conformal symmetry. And so from here, so later, I will classify this transformation based on this symmetry. So so imposing this, then you can infer that this leads to some particular constraint. I will derive this later. Okay, but this is something you may know. No. Yeah. Yes. Okay. Yes, I will derive this. But before going there, I want to mention one more thing. So first, the idea of conformal field theory would be that so it has some special symmetries, like this conformal symmetry. And then the idea is, so what can you learn just from these symmetries, even without knowing the details of the theory? So that's the idea of conformal field theory. So by using this symmetry, you can get a number of results regardless of the details of the theory. So that's the thing people want to learn in conformal field theory. And okay, there was one thing I wanted to mention, but maybe I skipped it. Yeah, let me skip this. So let's go here. So now your agenda is without knowing much detail about the theory, and what can you run? About CFT. So this is the main theme. So this is the theme. So I will first discuss this symmetry, conformal symmetry. I will elaborate on this, and then second, I talk about some property of E mu nu, which is energy momentum tensor. And then I talk about correlation functions. So the main task is actually to determine the form of correlation functions simply from this symmetry. So that's the idea of conformal field theory. And then, of course, I have to here. So I have to explain what's the players in CFT, and also what determines conformal field theory is the conformal field theory data. So these things I will talk about. And let's 5. So now, let's analyze this symmetry. Let's analyze the symmetry. So we consider, right, so this transformation I call F is, to be precise, and as I wrote there, and then epsilon is very small. So I work in infinitesimal transformation. So this is infinitesimal transformation. And so because I will work on infinitesimal transformation, this function phi of x, I also treat this as small transformation. And then this will be an exercise, but it's very simple exercise. So this is the condition for conformal symmetry. So what you get is plugging this in and expanding it, then you will find this. So this is the equation you get. Okay. So so the goal is to find this function as a function of x. So from this equation, what can you learn? You have h of x, which is arbitrary, so you can't gain much, right? But so next thing, actually this h is given by this f. So take trace. Yes, okay, so you have this tensor, rank 2 tensor, and then this is a matrix, right? Both sides, this is a matrix, and this is a matrix, and then you take the trace. And then, on the left-hand side, what you get is, okay, I write it. So this notation is, I use this notation. Okay, so this side, this is trivial. D, yes. D, yes, h of x. So you got that h of x is 2 over d delta x. That's what was here. Okay, so now you've got this equation, and then how do you find f? It's a good exercise. And you will find all these transformations. That will be the bottom line. Yes, so, well, so from here, how to proceed is not so trivial. So then what you do is take derivative. You take the derivative of this equation, and then you can show that if D is not 1. So you can show this. So this will be another exercise question. So let's say, okay, so this is at question 1, and so this will be at 2. So you can show this. And then here, what can you say about this function? No, it's second, so it vanishes on the two derivatives. So that would be actually linear function, yes? It's a linear function of x. So I parameterize this as, so I introduce some parameters, beta and alpha. So from here, you integrate. And I just give the answer. And you can check this is true. And 2x mu alpha x and x square alpha mu. That's one part. And mu plus omega mu nu x nu plus a mu. So if you take the derivative of this and then take the trace, you will find that this will give you this one. So you have alpha and you have beta, and the reason why there's D is when you take derivative, you contract the index and it gives you D, and so it's going to be beta. And this one is here because this is anti-symmetric. So if you take the derivative delta mu, then this index nu becomes mu, and if it's anti-symmetric, it's identically vanishing. And then you have constant. This is the integration constant. Okay, so now you know what they are because I mentioned it. So the first one is the parameter alpha characterizes special conformal. Yes, so this is the special conformal. Special conformal. And this one, dilatation. Yes. Obviously, this is rotation. Yes. Anti-symmetric tensor. And then this is the translation. Right. So then, how many parameters do you have? Okay, so special conformal transformation parameter is alpha mu. So how many parameters do you have? D, yes. So you have D and the dilaton 1, yes. And rotation, yes, because it's an anti-symmetric tensor of D by D anti-symmetric matrix. And so this translation is apparently D, yes. And so the total number is E plus 1, I think, E plus 2.
Isn't it D plus 1?
Yes, I think so, yes. Right. Good. D plus 2. Well, I think, wait, this should be right. Wait. Yeah, no, sorry. Yeah, no, it is true. I was, yeah. Yes, of course you can calculate, but the reason is, as I mentioned later, so this transformation forms a group which is D plus 1, 1, or SO D, 2. So this is a rotation matrix of D plus 2 dimensions. Yes, so that's why. Right, okay, so now I want to write down the generators. And then this is going to be the third question. So given these transformations, you can introduce generators. Conformal transformation. Okay, so let's start with translation. Yes, so I put I anticipating quantum mechanics. So the derivative is the translation, right? When derivative acts on the function, it will shift the x. So, okay. So maybe to be precise, when this acts on x nu, then it will split I nu. When this generator acts on x, it will give you a. So that means x is shifted by a. Okay, dilatation. So the idea is, so you have this transformation. Then if you put derivative, then it will give you generator. And dilatation then. Okay, so I give, maybe this will give a hint. So dilatation looks like this. And rotation. Right, rotation, because this is an anti-symmetric tensor, rotation looks like anti-symmetric tensor like this. So you know that this is the angular momentum x, x cross p. This is the x cross p. Special conformal from here. So as I said, the idea is to replace the parameters. Well, yeah, sorry. You have to put the derivative to this transformation. So so this is the form of special conformal transformation. So then I write down the algebra which you have to show in the tutorial. So these forms are closed algebra. Okay, this is going to be long, and so I write it later. Yeah, for example, this, and in the afternoon I will write it. All of them, but for example, I just want to so these generators form some algebra. And then finally, I want to just mention one thing. So this is SOD plus 1, or SOD, 2. So this is when I have Euclidean field theory. Euclidean. This is for Lorentzian. So the way to see it is to introduce mu nu. Then you introduce this L0 mu and minus 1 mu. And once you introduce these combinations of the generators, you will find that so this L mu nu is a d plus 2 dimensional version of this rotation. So what you have is, so this mu nu index goes from 1 to d, and then you have extra space indices, which is 0 and -1. So you have D plus 2. So that forms this D plus 2. And depends on the signature of your space. It could be D plus 1, 1. So it's space-like timeline and the space-like timeline. And so finally, I just mentioned this is related to ADS space. Because so this SOD SOD plus 1, 1 or SOD, 2 it's so this is isometry of ADS D plus 1. Because ADS space is defined by, let's say, x1 squared, xd squared, minus x minus 1 squared minus x0 squared is equal to minus r squared. So this is a hyperbolic space. And so this is an Untitled Chapter space. So you see that there's a rotation symmetry. So this case, it was Lorentzian. So you have SOD, 2 rotation symmetry. And in the case of the Euclidean, what I'm going to do is you have 2 times, and then we rotate one of them like this, and then so this is Lorentzian, and this is Euclidean. So then it will become a symmetry. So by this symmetry consideration, there is a sign that this conformal field theory may be related to Untitled Chapter space in some way. And that's so to define and to make it precise, then you get ADS CFT. So I guess I should stop now. And so I gave you 3 questions. And I will write down all the computation relations in the afternoon for this, and you have to check it. Right. So I couldn't go that far. So in the next lecture, I should be discussing correlation functions and hopefully conformal bootstrap and all these